Hi, I'm John. I'm a chemistry graduate student at UCLA, and now in this video we're going to be going over some chemistry topics. Hope you find this useful, and good luck in your course. In this video lesson we're going to be covering nuclear magnetic resonance, or NMR spectroscopy, particularly proton NMR spectroscopy. There's going to be a separate video that covers carbon-13 NMR, and so we're really just focusing on H-NMR right here. So here there's a layout of the different topics in order that we're going to be covering them, starting out with nuclear spin states and an applied magnetic field, what it means exactly by resonance, how we can determine equivalent hydrogens and pick them out in a spectrum, the definition of chemical shift and how that corresponds to different functional groups, signal splitting, which is arguably one of the more complicated concepts in this section, and then interpretation of some spectra. So there's, again, another video that covers how to actually solve spectroscopy problems given proton NMR data, an IR spectra, and mass spec data. And so we're not really going to be solving any problems in this video, just going over the general concepts. And then at the end there's going to be a summary. Okay. So you're already familiar from general chemistry with the concepts that an electron has a spin quantum number of 1/2 with allowed values of +1/2 and -1/2, and that a moving charge has an associated magnetic field. So in effect, an electron behaves as if it's a tiny bar magnet and has a magnetic moment. So this same effect holds true for certain atomic nuclei as well. So any atomic nucleus that has an odd mass number, an odd atomic number, or both also has a spin and a resulting nuclear magnetic moment. So the allowed nuclear spin states are determined by the spin quantum number that is dictated I here of the nucleus. And a nucleus with a spin quantum number of I has 2I + 1 spin states. Now if we look at H1 here, we see that the nuclear spin quantum number is 1/2, and therefore it has 2 allowed spin states. Note, for example, that C12, O16, and S32 here on the chart have spin quantum numbers of 0 and therefore only 1 allowed nuclear spin state. And these nuclei are inactive in NMR spectroscopy. Now within a sample that contains H1, atoms or carbon-13 atoms, the orientation of the nuclear magnetic moments associated with their nuclear spins are completely random. However, whenever they're placed between the poles of a powerful magnet of field strength B0, then interactions between the nuclear spin states and an applied magnetic field are quantized, with the result that only certain orientations of the nuclear magnetic moments are allowed. So, in other words, in the absence of a magnetic field, all the spins are in random directions. Under an applied magnetic field, then what happens is that the nuclear spin states are aligned either parallel or anti-parallel to the magnetic field direction. By convention, nuclei with spin of +1/2 are aligned with the applied field, and spin of -1/2 are aligned against the applied magnetic field. Now this one, the latter, is higher in energy. Now the most important NMR physical concept from the point of view of molecular structure determination is that the difference in energy between nuclear spin states for a given nucleus is proportional to the strength of the magnetic field that is experienced by that nucleus. And so, in other words, if you look at the chart on the right-hand side, the energy difference between the allowed nuclear spin states increases linearly with the applied magnetic field strength. Now let's talk about what's actually meant by the term resonance. So when nuclei with a spin quantum number of 1/2, such as protons, are placed in an applied magnetic field, small majority of the nuclear spins are aligned with the applied field in the lower energy state. When nuclei in the lower energy state are irradiated with electromagnetic radiation in the radio frequency range, then they absorb energy and the nuclear spins flip from the lower energy state to the higher energy state, the only other allowed spin state. Now, to visualize the mechanism by which a spinning nucleus absorbs energy and the meaning of resonance in this context, you can think of the nucleus as if it were really spinning. Now, when an applied field strength is turned on, the nucleus becomes aligned with the applied magnetic field in the allowed spin energy state. The nucleus then begins to precess, as shown on the left-hand side of this diagram. So what happens is that it traces out a cone-shaped surface in much the same manner as a spinning top or a gyroscope traces out a cone-shaped surface whenever it would precess in, for example, Earth's gravitational field. Now we can express this rate of precession as a frequency in hertz. Now if the precessing nucleus is irradiated with radio frequency electromagnetic radiation at exactly this precession frequency, then the two frequencies couple, the energy is absorbed, and the nuclear spin flips from a spin state of +1/2 to a spin state of -1/2, which is aligned against the applied field. So the spectrometer then detects this absorption of electromagnetic radiation and records it as a signal. And the process is quantized so that only electromagnetic radiation of precisely this correct frequency will cause the nuclear spin to flip. Now, a key physical principle for NMR is that circulating electrons induce a magnetic field. And this is the principle behind electromagnets and electric motors. So the direction of electron movement dictates the orientation of the induced magnetic field. Of equal importance to NMR, the converse is also true. So an applied magnetic field induces electrons to circulate, and the orientation of the field dictates the direction of circulation. The important point for our purposes is that an applied magnetic field induces the electron density of a molecule to circulate. The spin states of the underlying nuclei are in turn influenced to a small but measurable degree by the magnetic field that's created by the induced electron density circulation. Now, the circulation of electron density in a molecule in an applied magnetic field is called a diamagnetic current. And it turns out that a molecule's sigma bonding electron density is induced to circulate in a direction that causes a small magnetic field that directly opposes the applied magnetic field. Now, as a result of these opposing magnetic fields, the nuclei with the circulating electron density experiences a magnetic field that's slightly smaller than the actual applied field. So in other words, nuclei underneath circulating sigma bond electron density are shielded to a small degree from the applied field. Now, the degree of shielding depends on several factors, which we'll talk about a little bit later in the video. But what we want to establish now is that as the shielding becomes greater, the net magnetic moment that's present at the nucleus becomes smaller. So what happens is that the energy of the electromagnetic radiation that's required to bring that nucleus into resonance also decreases. So when we put all these together, we see that a nucleus that is more shielded is going to come into resonance at a lower frequency than a nucleus that is less shielded. Now, the difference in resonance frequencies that are caused by differing amounts of shielding is called the chemical shift. The differences in resonance frequencies among various hydrogen nuclei within a molecule that's attributed to shielding or deshielding are generally very small, but they are measurable enough so that you can get information about different functional groups on the molecules. Now, typically when reporting NMR data, you show it in a chart like this, in which the lower axis is the chemical shift in parts per million. And it's customary to measure the resonance frequencies of individual nuclei relative to the resonance frequency of nuclei in a reference compound. Now, the reference compound that's most commonly used is tetramethylsilane, or TMS. And this is assigned, the hydrogens in this molecule are assigned a chemical shift of 0 ppm by convention. And so for other molecules, the chemical shift in parts per million is defined as the frequency shift from either the hydrogens or the carbons, if you're looking at carbon-13 NMR, in TMS, divided by the operating frequency of the spectrometer. Now, if a signal is shifted towards the left of the chart, this is a larger chemical shift, we say that it is shifted downfield. A downfield shift corresponds to decreased shielding around the nucleus, or deshielding. If the signal is shifted towards the right, This has a smaller chemical shift, and we say that it is shifted upfield and therefore corresponds to increased shielding around the nucleus. So, given the structural formula of a compound, how do we know how many signals to expect in its proton NMR spectrum? So the answer is that equivalent hydrogens give the same proton NMR signal, and non-equivalent hydrogens give different NMR signals. So equivalent hydrogens have the same chemical environment. So hydrogen atoms are equivalent based on a couple of different conditions. Basically, that number one, they are bonded to the same sp3 hybridized carbon atom, and that carbon atom can rotate freely at room temperature. Or they are related by symmetry, namely a plane or a point of symmetry in the molecule. So, for example, how many equivalent hydrogens would there be in 2-methylpropane and 2-methylbutane? Well, 2-methylpropane contains two sets of equivalent hydrogens. There is one tertiary hydrogen that I pointed to here, and a set of 9 equivalent primary hydrogens. So again, there are two sets of equivalent hydrogens in this molecule. So what would happen is that on a proton NMR spectra, you would only see 2 peaks. Now 2-methylbutane, on the other hand, contains 4 sets of equivalent hydrogens. Again, there's one tertiary hydrogen, a set of 2 equivalent secondary hydrogens, a set of 3 equivalent primary hydrogens, and then a set of 6 equivalent primary hydrogens. So an NMR spectrum of this molecule would have 4 peaks. Some organic compounds can give just a single spectrum or a single peak on one spectrum. For example, cyclopentane, all of the hydrogens attached to each one of these carbons are equivalent. Also, in 2,3-dimethyl-2-butene, all of these hydrogens are equivalent as well. So again, these are each just going to have a single signal in the H-NMR spectrum. Molecules with 2 or more sets of equivalent hydrogens are going to give rise to different resonance signals for each one of those. Okay, so the number of signals in an NMR spectrum gives us info about the number of equivalent sets of hydrogen atoms. Now, the relative areas of those signals give us information about the number of equivalent hydrogens that give rise to each signal. So the vertical rise of the line of integration over each signal is proportional to the area under that signal, which in turn is proportional to the number of equivalent hydrogens that give rise to it. So this is an example proton NMR spectrum of tert-butyl acetate. There are 2 peaks here attributed to the protons in this molecule, or the equivalent hydrogens. The peak here at 0 ppm is just our reference. And the relative integral of each one of these 2 peaks at the chemical shift of about 1.5 and close to 2 here is 1 to 3. So these are not numbers that you're generally going to be able to deduce yourself given a plot like this. They're generally going to be given to you. And the actual numbers that are given don't really matter. It's just the relative value. And so they could be multiples of this. But these values are not surprising given the fact that you should have 2 sets of equivalent hydrogens. And so you have the hydrogens attached to these methyl groups, and then this one other set on the left-hand side of the molecule. And as you can see, there are 3 hydrogens to 9 hydrogens. And so it's a 1 to 3.